Welcome everyone. For today's prep, we're going to look at an applied optimization example. And this is going to put to use a lot of our optimization techniques that we've been developing. And in particular, we're going to use our strategy for solving those constrained optimization problems that we looked at in the last section. So the example we're going to look at today, let's read through it. And it says we want to plan a rectangular garden along one side of a house, and we're going to fence in the other three sides. Okay. And we want to find the dimensions of the largest garden that can be enclosed using 40 feet of fencing. So this is our problem here. And our strategy for solving this is going to be the constrained optimization steps that we looked at. Now we're going to add one extra step here right at the beginning. And a lot of the examples for these applied problems that we're going to be considering are kind of geometric in nature. So it helps, kind of step zero, just to kind of see what's going on. Draw a diagram. So usually this helps. All right, so let's go back through the problem here and look for kind of keywords that describe the geometry of what we're doing. And we see it right here. We want to plan a rectangular garden. So let's get a rectangle going. And what we want to do in this case is one side of this garden, one side of this rectangle is going to be planted alongside a house. So let's just pick one of the sides. So let's maybe make it this side over here. And this is where we have our house. So when we go to fence in the other three sides, we're going to put a fence here, we're going to put a fence here, and then we're going to put a fence here. All right, so we've got our garden going. And as we kind of draw these geometric objects down, you want to introduce variables that describe the object. So we have a rectangle. So we know for a rectangle, there's kind of two different dimensions, the length and the width. So let's call one of them X and one of them Y here. You could use L and W if you wanted to, but X and Y are kind of standard variables. And for a rectangle, we know opposite sides have the same length. So this side is also X and this side is also Y. All right, so for our constrained optimization, the first real step is figuring out what the objective and the constraint equations are. So the objective, this is what we want to maximize or minimize. So again, we want to go back to the wording of our problem and kind of look for where it indicates find the maximum of or find the minimum of. And here it says we want the largest size for our garden. Okay. So the question is, how do we measure the size of a rectangle? And we do that with area. So our objective is going to be area. So our largest garden, that's going to be our objective. All right, so how do we find the area of a rectangle? Well, just length times width. So in this case, it'll be X times Y. And just to abbreviate this, we'll call the objective A for area. All right. So now we want to find our second equation, and this is the constraint. So we want to go back through the problem and look for wording that kind of puts some limitation on what X and Y can be. And so if we didn't have any constraints here, we wanted to make this garden as large as possible, well, we would just make X and Y as large as possible. So we want to go back to the wording of our problem and look for kind of additional information, usually in the form of a constant, that kind of puts some limitation on what we can do. And in this case, we see it right here. We're only going to be using 40 feet of fencing. So that's going to be our constraint, the amount of fencing. And we know that this should be equal to 40. All right, so how much fence are we going to need to fence in the three sides of our rectangle? Remember, we don't need one over here. So for our rectangle, we don't need a fence on the side that's next to our house, but we do need fencing for this side, for the other three sides. All right, so let's figure out how much fencing are we going to need for this side. Well, y describes the length, so we're going to need y number of feet for that left side. Then we're going to need x number of feet for the bottom side here. And then we're going to need y number of feet for the right-hand side. So we're just going to add up y plus x plus y. And usually a good idea, try to simplify. So in this case, we can add up our two y terms here. And we get 40 is equal to 2y plus x. All right, so this is usually the hardest part for these applied optimization problems. It's reading the word problem and kind of extracting the information and forming the equations that we're going to kind of do our optimization on. So this is usually the hardest part for these. And a lot of times it helps. Draw a diagram. All right, so now that we have our two equations, we've got our objective, we got our constraint, now we kind of go through our usual constrained optimization steps. So step 2 then is to solve the constraint equation for one of the variables, so whichever one is easier. And in this case, there's not too much of a difference, but I think it's a little bit easier to solve this for x because we don't have a coefficient that we'd have to divide by. So let's solve our constraint equation for x. And all that means is we're going to subtract 2y from both sides. So we get x is equal to 40 minus 2y. And then the next step is we plug this result into our objective. And that's going to give us a one variable function. So we're going to plug it into our objective equation back here. So our objective is this area function, x times y. And instead of that x, we're just going to fill in what we know x should be equal to. And we get area is 40 minus 2y times y. And again, all we've done is we've changed this x to what we know x is from our constraint. And at this point, what we have is a one variable function. So one variable functions, we have the strategy now to actually optimize these. And we know that's going to involve finding and classifying the critical numbers. And that usually involves the first derivative and usually the second derivative as well for the classification part. So to help us with the differentiation, let's actually multiply this out first. So we get 40 minus 2y squared. All right, so now we're ready. Let's find and classify our critical numbers. So let's start with the finding. And we know for finding critical numbers, there's two ways we can have a critical number. Either the first derivative is equal to 0, or the first derivative does not exist. All right, so let's figure out, well, we need to first figure out the first derivative. So if we do that, we end up with a prime is 40 minus 4y. And if we're looking, there's no division by 0 here. So we differentiated our a function here. There's no division by 0. There's no negative exponents. So we're not going to have any critical numbers from this being undefined. So then we just set this equal to 0. And we add 4y to both sides. So 40 is equal to 4y. And then if we divide by 4, we get y is equal to 10. All right, so that's our critical number. So if this area function is going to have a max or a min, it can only happen there. So now the next step is to classify our critical number. And the quickest way to usually do our classification is with the second derivative test. So when we do our classification, state which test you're going to use. You could also use the first derivative test, but we're going to use the second derivative test. And as the name suggests, we're going to need a double prime, our second derivative. So if we plug it, or if we differentiate, we get -4. And the way we actually perform the second derivative test is we take our critical number, which in this case is y equals 10, and we plug that into our second derivative. And in this case, our second derivative is a constant function. So we get out -4. And negative second derivative means concave down. Draw the concave down shape to help remember what the test says. And we have a local max. And technically, because we only found one critical number, not only is this a local max, it's actually the absolute max. And again, the reason there was we only had one critical number. Okay, so this classification, you can almost use this as a check, because what did the directions say? We wanted the largest. So that's a maximum, and that's precisely what we found. We're finding that we have an absolute max. All right, so those agree. So that's just a kind of a way to check your answer. We're not going to give any trick questions or anything like that. So whatever classification you get really should match up with what the directions are saying. All right. So let's just make sure then, the last step is to make sure you actually answer the question. So what did the question actually ask us to find? It said, find the dimensions. So what are the dimensions of our rectangle? Well, these are the x and y values. So we found the y value already. So we need to find the x. And we have a few options. We could go back to our constraint and kind of use that to solve for x. But we've actually already solved for what x is equal to. So we can just plug our y value into here. So we know y is equal to 10. And we know x is equal to 40 minus 2 times y. So if we plug our y value in there, we end up with 20. All right, so that's it. And again, for these applied problems, one thing with answering the question, we just want to make sure, are units given? If units are given in the problem, then our answer should have units. And in this case, yeah, we're measuring length here in terms of feet. So our units for x and y are going to be feet. So this is an easy thing to forget. Make sure your answer includes units if units are given. So you don't want to forget the units. All right, so we're going to try a few more of these in class, but this is generally the idea. A lot of this is we're just kind of putting the pieces together now. And what's really new in this section is really the first part of cooking up these objective and constraint equations based on the actual problem. All right, so we'll see some more of these in class. We'll see you then. Bye-bye.